Let's begin with a gas, one of the fundamental states of matter. Unlike solids or liquids, the particles in a gas are far apart and move freely. They're constantly moving in straight lines until they collide with walls or each other, each following Newton's laws of motion. To describe how gases behave, we need to track a few important variables. Let's explore each one and see how they work together. To understand how gases behave, we study four essential variables. Pressure, the force gas particles exert when they collide with container walls. Volume, the space the gas occupies. Temperature, which reflects how fast the particles are moving, their kinetic energy. And moles, which simply count how many gas particles we have. Each of these variables influences the others in predictable ways. By changing one while holding others constant, we uncover the fundamental laws of gas behavior, the building blocks of the ideal gas law. Let's begin with Boyle's law, the relationship between pressure and volume. We'll hold temperature and gas amount constant. Now, we compress the gas by pushing the piston downward. As the available volume shrinks, gas particles collide with the walls more frequently and with the same energy. This results in a rise in pressure. Boyle's law tells us that pressure and volume are inversely proportional. When one goes up, the other goes down, always keeping their product constant. Now, we explore Charles's law, the connection between temperature and volume, while keeping pressure constant. As we heat the gas, the particles begin to move faster, they carry more kinetic energy. To maintain the same pressure, the gas must expand, giving particles more room to move and reducing the frequency of wall collisions. Charles's law shows that volume is directly proportional to temperature, as long as pressure and moles stay fixed. Let's add more gas while keeping pressure and temperature constant. This is Avogadro's law. As we introduce more particles into the system, the number of collisions with the walls would increase, unless the volume increases too. To maintain constant pressure, the volume expands, allowing particles to spread out. Avogadro's law tells us that volume is directly proportional to the number of moles, or in simpler terms, more gas means more space is needed. Finally, we look at Gay-Lussac's law, the link between pressure and temperature, with volume and moles held constant. When we heat a gas in a rigid container, the particles move faster but don't have more space. This means they strike the container walls more often and with greater force, raising the pressure. Gay-Lussac's law tells us that pressure increases directly with temperature when volume stays fixed. This is exactly why pressure builds in a sealed can left in the sun. Let's begin at the molecular level. Gas particles are constantly in motion, bouncing around and colliding with the walls of their container. Each collision exerts a tiny force, and when you add up all these microscopic impacts, they result in the pressure we observe on a macroscopic scale. This microscopic behavior is described by the equation: pressure times volume equals capital N times K sub B times temperature. Here, N stands for the total number of gas particles, K sub B is Boltzmann's constant, and temperature reflects the average kinetic energy of the particles. This equation connects individual molecular motion to bulk properties like pressure and volume. Instead of counting individual molecules, we usually group them into moles. Using Avogadro's number, we write capital N equals lowercase n times N sub A. Here, lowercase n is the number of moles, and N sub A is Avogadro's number, approximately 6.022 times 10 to the 23rd particles per mole. This conversion allows us to go from counting molecules to using a more manageable unit. Now, if we substitute N times N sub A into the earlier equation, we get pressure times volume equals N times N sub A times K sub B times temperature. Since the product of Avogadro's number and Boltzmann's constant appears so frequently, we define it as a new constant, R sub U, the universal gas constant. So we arrive at the familiar form of the ideal gas law. Pressure times volume equals N times R sub U times temperature. Sometimes, it's more practical to describe the gas by its mass instead of the number of moles. Using the molar mass capital M, we can write N equals lowercase m divided by capital M. Here, lowercase m is the total mass of the gas in kilograms, and capital M is the molar mass in kilograms per mole. Substituting mass over molar mass into the ideal gas law, we get pressure times volume equals lowercase m divided by capital M times R sub U times temperature. We define R, the specific gas constant, as R sub U divided by m. This constant is different for each gas and allows us to write the equation in a mass-based form. Pressure times volume equals mass times R times temperature. To go one step further, we introduce the concept of density, represented by the Greek letter rho. Density is defined as mass divided by volume. If we divide both sides of the equation by volume, we get pressure equals rho times R times temperature. This version is especially useful in engineering, where we often work with density rather than mass or moles. Finally, we can define specific volume, represented by lowercase v, as the inverse of density, that is, 1 divided by rho. Substituting this into the previous form, we get pressure equals R times temperature divided by specific volume. Rewriting, we arrive at pressure times specific volume equals R times temperature. This compact version is common in thermodynamics and fluid mechanics. Let's summarize all the different forms of the ideal gas law and the important constants we've discussed. Assumption 1. Gas particles are treated as point-like. They are so small compared to the container that we assume they occupy no volume. This means all of the container's space is available for the particles to move freely. This assumption works well when gas is sparse. But under high pressure, particles become crowded and their size matters, reducing the free space. Assumption 2. We ignore any attractive or repulsive forces between particles. They move in straight lines until they collide. No long-range forces act between them. This simplifies the motion greatly. In reality, particles do attract each other, especially at low temperatures. This leads to deviations from ideal gas behavior. Assumption 3. The gas must be dilute. This means the particles are far apart, making interactions rare and justifying our previous assumptions. In the dilute limit, all the container volume is available and molecules rarely collide. If gas becomes dense, particles are more likely to collide or interact, violating ideal behavior. These three assumptions, point particles, no intermolecular forces, and low density, form the foundation of the ideal gas law. They help us model gases accurately under normal conditions. But in extreme situations, like high pressure or low temperature, we need more advanced models. Let's review the big picture. The ideal gas law connects pressure, volume, temperature, and the amount of gas in a single elegant equation, PV equals nRUT. We can visualize the fundamental relationship as an equation. Let me show you how pressure times volume divided by the number of molecules times temperature equals Boltzmann's constant. First, let's see Boyle's law, the relationship between pressure and volume. When temperature and number of molecules stay constant, pressure and volume are inversely related. Next is Charles's law. Volume and temperature are directly proportional when pressure and number of molecules remain constant. Avogadro's law shows that volume is proportional to the number of molecules when pressure and temperature are held constant. Finally, Gay-Lussac's law connects pressure and temperature directly when volume and number of molecules stay constant. Together, these four relationships form the complete picture. All four gas laws are unified in the elegant equation we see here. These three forms represent the same fundamental relationship. The molecular form uses capital N for the number of molecules and Kb as Boltzmann's constant. The molar form uses lowercase n for the number of moles and Ru as the universal gas constant. The mass-based form uses m for mass and R as the specific gas constant, which varies for each gas. The equation shows the molecular form with capital N representing the number of molecules. However, in engineering and science, we also commonly use the molar form with lowercase n for moles. Here, P is pressure, V is volume, N is the number of molecules, and T is temperature. But remember, this equation depends on key assumptions. We treat particles as having no volume, assume no forces between them, and say that collisions are elastic. It also works best when the gas is dilute and molecules are far apart. Under normal conditions, low pressure and high temperature, these assumptions hold, and the law gives accurate results. But when gases are compressed or cooled, particles interact more, and the ideal gas law begins to fail. Still, the ideal gas law is a powerful approximation that underpins much of thermodynamics, chemistry, and engineering. It's the starting point for understanding how gases behave and where more advanced models begin.